All righty, well, I guess we can get started. Welcome, everybody. Today's talk for the MTV Nuclear Engineering Summer School is going to be given by Dr. Ethan Klein. Dr. Klein is a recent graduate from MIT in the Department of Nuclear Science and Engineering, where he did his thesis work with Professor Donagolian on nuclear transmission resonance analysis. And he's a soon-to-be student at Stanford's Graduate School of Business. So Ethan, whenever you're ready, take it away.
Terrific. Thank you very much for the intro, Colton. Great to have everybody online here. So let me get this screen shared for you all. Terrific. So thank you all for being here today. I want to talk to you guys about my PhD research on using a portable neutron generator to do identification and quantification of different kinds of nuclear material. It's my understanding that this is Neutrons Week for you guys. So you have heard about some of the other techniques that folks have been using. So I'll give a little bit of a physics background of our technique, discuss some of the other possible techniques that one may use for identification and quantifying nuclear material, and then we'll go through how the technique works and dive into some of the results. That's essentially what I just have on the outline here. The two main applications that I would like to discuss with you guys, the first is going to be for detecting and quantifying uranium, including in the presence of different shielding materials. And the second is going to be for arms control verification. Go over a few conclusions, make a few, just say a few words about future work for this project. And hopefully it'll be an informative and fun discussion that we'll have afterwards. So just to kick things off, give you kind of the research question that we're trying to answer in our group with this research topic is, can we develop a portable system for identifying, quantifying nuclear material? And can we build this system such that it could be used on site for a range of different arms control, nuclear non-proliferation, and safeguards objectives? So what are the kinds of applications that we could envision where you would really want to have a tool to perform isotopic identification and quantification? I'll list three out here. First is for nuclear safeguards. Second is for arms control verification. And the third could be something like disaster response. You can imagine after Fukushima disaster, for example, that you'd want an ability to identify, quantify these unknown debris materials. So the associated questions with each of these different areas that we're seeking to ask and to answer using our nuclear techniques is, how do we detect undeclared nuclear activity? Second is, how do we verify compliance with arms control agreements? How do we know that when a country says this is a nuclear warhead or it's not a nuclear warhead, that we can verify that and say, yes, they are indeed correct. They're not tricking us. And for the third is, how do we analyze nuclear material in unknown forms? So sometimes we have the privilege of being able to perform safeguards measurements on fuel assemblies, which are well characterized, well understood. We know what they should look like, but sometimes you don't have that luxury and you want to have an ability to still characterize materials that may be unknown forms, unknown materials. So the main point from this slide is just to say that detecting and quantifying nuclear material is important across a range of different application areas. So then you probably have heard a bit about this over the past few weeks, but there are different properties of nuclear material that can help us get these signatures that we would need to identify and to quantify them. So I'll just put two different isotopes of interest. We'll put here plutonium oxide 238, along with high enriched uranium. And just the point I want to make here is that they have very different radiation signatures. Plutonium oxide gives off thousands of neutrons per second per gram of material, whereas high enriched uranium gives off barely any, even for kilogram quantities. Furthermore, they both have gamma emissions, but those gamma emissions are at very different energies, and again, with differing intensities. And so just because we have nuclear material here of different forms, different geometries, it doesn't mean that we're going to necessarily be able to use the exact same detection techniques for one as we would use for the other. So the main point here is we have a whole range of these different nuclear detection techniques, some of which are better suited for some materials with certain emissions and for others with different isotopic signatures. Here's just a quick overview. Some of these techniques you may have heard before. Just on the left-hand side, the names of the techniques, and then on the right-hand side here, for the active interrogation, discuss what are the means of probing the material, what is the signature that we're trying to detect, and what is the actual underlying signal. So here you see we have a few different fission-based techniques, such as fast neutron multiplicity counter. You see the one that we'll be discussing today, NRTA, or neutron resonance transmission analysis, and that I'll just put on our little laser pointer to show you just there. But there are other techniques that you can use. You could induce signatures using gammas and look at the gammas coming out, or you could even do passive techniques. So main point here is just there's a range of different material analysis techniques. I'll go into some of the pros as well as the cons of using NRTA, which is the subject of this talk. So what are some of the limitations of existing techniques that are currently used for performing this identification, quantification of nuclear material? One of which is limited isotopic range. So as we showed before, uranium, for example, has very low neutron signatures, whereas a lot of the plutonium isotopes have very significant neutron signatures. So you can imagine if you put a neutron detector to try to detect these materials, you wouldn't see a signal for the uranium, but you very easily could for plutonium. Here we have just a table of all of the different spontaneous fission neutron yields for a range of different isotopes which are of interest to us, and I'll just highlight a few, show the fission yields for the thorium and uranium isotopes, and you see that they're super low, right? They're 1e minus 3, 1e minus 4 neutrons per second per gram. Whereas for plutonium, they're maybe 6 orders of magnitude higher. So that's already some kind of limitation if we're wanting to use a passive neutron detection technique for our ability to detect uranium. Another limitation is that your technique may not have isotopic specificity. So although you may be able to get a signal from both uranium and plutonium relative to background that says, hey, I think I have some material of interest here, you may not be able to distinguish between those specific isotopes because the signal won't be that different for the two. So you may be able to detect total fissile mass without differentiating between uranium and plutonium, which may be a capability that you would like to have. A third limitation is a lot of these techniques are shielding dependent. So if you take a chunk of uranium, it has gamma emissions, which you can detect with a gamma detector, but maybe if you put just a little bit of lead shielding around it, if those gammas are low energy enough, they're going to get captured in the shield, and it's going to be very difficult for you to measure any significant counts in your gamma detector. And just to answer very quickly, the previous question I saw about high enriched uranium comprises which uranium isotopes. The answer there is high enriched uranium is primarily uranium-235. Technically, it's defined to be anything greater than 20% uranium-235. But for weapons grade, what you'd use high enriched uranium for nuclear weapons, for example, would be around 93% of uranium-235, and then approximately 6.5% of uranium-238. So natural uranium has roughly only 0.7% of uranium-235. So that you have to really, really enrich it to get it to high enriched uranium. Great. So here on this plot, what you can see is the impact of the thickness of lead on the transmission of gamma rays of different energies. So here we see the 200 keV along with the 1000 keV or 1 MeV. And you can see that for those low energy gamma emissions, it just takes a little bit of lead to completely kill your transmission. So that's a big limitation. 200 keV is roughly what uranium-235 gamma emissions give, and 400 keV is what you can get from plutonium. So you can see here that there's a differential between uranium and plutonium and the ability of lead shielding to shield those radioactive signatures from being detected. And the fourth limitation of a lot of these existing techniques is that those low energy gammas, for example, from uranium that are emitted from the inside of your uranium sample, if it's a sufficiently thick target, they're not ever going to escape the material itself. And so the measurements that you're doing with the gamma detector really are only probing the external shell of that uranium material. And so what you can see on the right-hand side of the slide here is that you could imagine replacing the interior of that uranium with something much less worrisome for nuclear non-proliferation concerns, such as tungsten, for example, which would have a similar density as uranium. And maybe you could divert that uranium for illicit uses, and you would still see a very, very similar, if not exactly the same, signature in your gamma detector. So these are limitations of existing techniques, which led us to look to other techniques that may not suffer from all of these. So the question that we asked ourselves are there techniques that exist which are suitable for a broad range of isotopes, are isotope specific, and are capable of analyzing thick nuclear materials? And the answer we came up with is yes, it's NRTA, which is the subject of this talk, and that stands for Neutron Resonance Transmission Analysis. And we'll go through the different steps of that over the subsequent slides. So just by way of background for you guys, start out by theory of neutron resonances. So let's say we have a target nucleus X, isotope A of element X. We'll take a neutron, we'll put that neutron incident onto the target nucleus, and what comes as a result? There's a likelihood of forming a compound nucleus, where it's kind of this state that's formed between the two, an intermediate step of this isotope A+1, and then there are a few different pathways that we can go from that compound nucleus. The first is if it's fissile material, that neutron could induce fission, and you'd see a splitting apart of that compound nucleus with the emission of neutrons along with gamma rays. Another option is you could have elastic scattering, where the neutron is re-emitted from the compound nucleus without transferring any of its energy to the target. Another option is radiative capture. The compound nucleus says, I actually liked holding on to this neutron. I'll have to relax by emitting some gamma, but I'm going to keep that neutron and hold on to it. So these are a few of the different processes that can happen when you have a neutron incident on a target nucleus. Now, what governs the likelihood of those different interactions and how likely even it is to form a compound nucleus in the first place? So we can imagine here looking at on a y-axis, the energy of the total system. On the left-hand side, we have the energy levels for the state of the target nucleus plus the neutron. And on the right-hand side, we can see the energy levels for that isotope A+1 of element X. And this is the basis of the NRTA technique, is that if you fine-tune the energy of your neutron such that it matches one of those states in the compound nucleus, then what we can see is we end up getting an increased likelihood of interaction, an increased likelihood that we form that compound nucleus. And so we see peaks in our neutron cross-section as a function of that neutron energy. And so those peaks in the cross-section are going to correspond to the quantum state, quantum levels of that compound nucleus. So what we expect to see then is that there at specific neutron energies for specific isotopes, we're going to see a much, much higher likelihood that that neutron will actually interact rather than passing through without being attenuated without having any interaction with the target nucleus. Great. So what does that look like for a range of the different isotopes of uranium and plutonium that are of interest to us? Here I'm showing the total cross-section as a function of the energy of that incident neutron, just in the range of 1 eV to 50 eV. And so what's the first thing you notice for all these isotopes is they all have this very rich structure, right? These aren't flat lines that we see on this plot, but we see all these different peaks for each of these isotopes. And furthermore, they're unique for the individual isotopes. So no one of those colors matches exactly the spectrum of another one. They may have some overlapping peaks, but across the entire spectrum, they're totally unique. So first conclusion here is that your resonances are isotopically unique for special nuclear material. And when I say special nuclear material, I mean the nuclear material that's of most concern for different non-proliferation concerns. What else do we see? Well, if we plot non-uranium, not plutonium, but rather the different organic components and common metals that you would use to shield nuclear material, such as aluminum, iron, and lead, what you see is we don't see any signatures. We don't see any of those energy-dependent features that we saw for the uranium, plutonium, and thorium isotopes. So this is something that's helpful. Why? Because it tells us that even if we have shielding material around some nuclear material, we won't expect to see any energy dependent features. And so if we do see any of those energy dependent peaks, we may be able to associate them back to the uranium or plutonium, which we're trying to identify. So this is very helpful because it means that this technique should be less dependent on the shielding of the material itself. So how many different isotopes are roughly have resonances in the range where we think that we should be able to analyze them using our technique? Well, here I show the periodic table along with just a little key guide here for what energies those neutron resonances show up at for the different elements. Now, for a system that we develop, we can probably measure stuff up to around 100 electron volts, but that's probably the upper limit. So highlighted in red here are all of those elements that have neutron resonances below 100 electron volts. And many of them even have below 10 electron volts, which is very easy for us to see using the system that we've developed. So the first thing to notice here is we're not great at being able to detect those low Z isotopes or elements that are higher up on the periodic table, but those lower down, such as the lanthanides, the uraniums, the plutonium of the actinide series, all should be able to have resonances which would be observable to us using this technique. So how does the technique itself actually work? We're going to look at just a simplified cartoon and step through that. So you start on the left-hand side there with a neutron source. You have a moderator to slow those neutrons down, the target of which you're trying to infer its isotopic composition, and then a neutron detector to detect those neutrons to make it through the target. And as I'm going to walk through the different steps of the technique, let's just keep track of the distance the neutrons traveled, the time at which it took the neutron to travel those different stages, and the energy of the neutron. So to start things off, step one is to generate neutrons. If we want to look at neutron transmission, we have to have a neutron source. Now, the generation of those neutrons is going to take some finite time. So if we start at a time t0, it's going to be some time t pulse that it'll take to generate those neutrons. And for us, because we use a portable neutron generator, those neutrons are generated fast. So they're coming out with 14 mega electron volts. So much, much higher energy than that energy range at which I showed you previously, where the signature is that we're really interested in. So we need to slow those neutrons down. That's why step two here is neutron moderation, or slowing down of those neutrons in a moderating material. For our setup, we use plastic, simple high density polyethylene to do that. And so the neutrons will take their time, they'll bounce around in that plastic, and eventually we'll have some neutron flux directed towards our target, but now they're going to be in epithermal energy range. So instead of 14 million electron volts, they're now going to be down in the range of 1 to 100 electron volts. And that's exactly the energy range of interest to us, where we saw those resonances, which we could use as a signature to detect and determine the composition of potential nuclear material. Now, those neutrons are going to take some moderation distance, d mod, to moderate, and we'll have to account for that. Now, the next step is that some fraction of these neutrons are actually going to be transmitted through the target, and some will be attenuated. Now, how do we determine that? Well, the calculated transmission is just going to be the ratio of the neutrons that make it through the target compared to that incident neutron flux that we sent into the target. So that ratio is going to be an exponential attenuation that's going to be based on a few different factors. It's going to be based on I here, the different isotopes present in the target, the densities of those individual isotopes, the total cross sections for those isotopes, which are going to be a function of energy, as we saw in the previous slide, and also the thickness of those independent layers. So the main thing to note here is that the transmission of neutrons at specific incident neutron energies is going to be highly dependent on the target composition. That's very helpful for us if that's what we're trying to infer. So step 4 now is to actually detect those neutrons using a neutron sensitive detector, and those are going to produce a signal at time t signal here. So now that we've detected neutrons which have made it through our target as a function of energy, how do we actually back out that neutron energy? Well, we can do this using a time of flight technique. So if you remember from maybe your first year physics, you learned energy is 1/2 mv squared, velocity is distance over time. So here, if we have the known distance that that neutron traveled, that moderation distance, along with the TOF, the time of flight distance for a fixed distance, we can take out the T signal, subtract out the time it took to produce those neutrons, and we can back out the energy of that neutron using this very simple formula. Step 6 is going to be to actually calculate the transmission. So what does it look like? What do those counts look like in our detector? So what we show here is the time of flight on the x-axis, the time referenced to t0, at which point we're getting those neutron counts in our detector, and we're just making a histogram plot of those. If we had no target present, we'd see exactly that black line. We'd see essentially a 1/energy spectrum characteristic of the neutron moderation process. If we had a non-resonant target, something like lead or organic material like plastic, we're going to see an overall attenuation of the signal, maybe 10 or 20%, but we're not going to see any of those energy independent features. Now, if we had a resonant target, imagine if we had a uranium metal or plutonium oxide, we would see both an overall attenuation of that signal, an overall lowering of that signal, along with some of those energy dependent features. Now, as we showed on just a few slides back, if we take the ratio of the red to the black and the blue to the black, we can get the transmission. And the transmission for that non-resonant target will be just a flat line. For the resonant target, though, we're going to see those characteristic dips at specific times. Because we're able to associate those times with specific neutron energies, if we see a dip in our transmission spectrum, we know that there must have been a peak in the interaction probability at that specific neutron energy. We can then look that up in our library of nuclear data and associate each of those different dips in our transmission spectra with individual isotopes, allowing us to figure out the composition. So we can calculate a neutron transmission. We can convolve that with our system resolution function just to account for the fact it's not a perfect setup. And that gives us a kind of calculated actual transmission as a function of neutron energies for a predicted isotopic composition. We can then minimize error by kind of varying what we believe the isotopic composition of that target is to be, minimize the error in that, the squared error in that, and that gives us a predicted isotopic composition of specific isotopes and their abundances. And so that's how the technique NRTA works. So with that in mind, let's step through what the design of the system actually looks like. And then let's start digging into some of the data and seeing how good of results we can get using this technique. So a few of the advantages of NRTA, I'm just showing you here actually the first paper on NRTA in 1975. To my knowledge, this was the first time somebody used neutron transmission as a means of inferring the composition of a nuclear material. And here what we're looking at are that transmission spectrum for low enriched uranium fuel. And so what you can see in those shaded dips are those corresponding to uranium-235. And so what that allows you to do by analyzing the area under those dips and doing that fitting technique we just discussed can let you to figure out what's the enrichment of that nuclear fuel. And hence for a safeguards application, is that what the host country may have told us, or is there maybe something fishy going on? So what are the advantages that were laid out nearly half a century ago by the authors of that paper? Well, they noted a few of them. The first was it gives an absolute measurement of the uranium content. The second is it works even in situations where you have highly radioactive samples. Third, it can be extended to a range of different isotopes of interest. And four, it's principally non-destructive. It doesn't fundamentally lead to the destruction of the nuclear material, but leaves it intact. So in conclusion, this technique, neutron resonance transmission analysis, is isotope specific, non-destructive, and it's applicable to a broad range of nuclear materials, even in high radiation environments. So what's the state of it today? Well, there's a bunch of cool different folks working on these techniques. There are folks doing it with laser-driven neutron sources, which lets you get very, very short neutron pulses and very, very high resolution. Also have folks who are doing this high precision 3D density measurements, where they're doing able to get these kind of slices, very, very thin spatially resolved slices of individual isotopes within small targets here, nuclear fuel. The main challenge for this is that these require really, really large experimental facilities. So over here, you can see just how large a person is and how large the experimental scale is relative to that. So the main focus of our work is, can we actually use this technique, but can we do it in such a way that we could do it in a portable setup that you could actually use it for safeguards and arms control applications where you really need to bring your interrogation setup on site. So very briefly, let's just discuss the system design and then we'll go to some results. So here's what the whole system looks like. It's just over 2 meters wide. We have our DT generator. That's a portable DT generator, which uses DT fusion as a means of producing neutrons. And those neutrons are produced here at the tritium target plane. We use a lead multiplier to leverage N2N reactions. We can actually multiply the neutrons that are coming out of the neutron generator. And then we use this high density polyethylene moderator to slow the neutrons down. Now, a fraction of those neutrons will be transmitted through the target object and will be detected here in our neutron detector, which operates using a lithium-6 detection mechanism. We have to add a bunch of shielding from boron carbide and cadmium foil as well, just to reduce the background signal that we get in our detector. But overall, it's a pretty compact setup. Both the setup on the left and that on the right here both weigh roughly 50 to 60 pounds. So all in all, you could fit everything into a few suitcases and perform this in a portable manner. Now, just to show you what it looks like in person, here's an actual diagram of that setup. And so you'll see all the same components we saw on the previous slide. Over on the left-hand side here is a DT generator with the lead and the plastic in white. And on the right-hand side here, you see the detector shielding box situated on a table, and you just place the sample just in front of the collimator right there. So what does this signal actually look like that we see in our detector? Well, what we can do is to plot as a function of time of flight on the x-axis, and on the y-axis, we can look at the energy of the independent counts that we get, and we can make a 2D plot here. First thing you're going to notice is this really kind of, bright spot at a very short time of flight. So what is that? That's the actual pulse. So when we produce our neutrons, the fast neutrons, they're going to scatter all over the place, and they're going to produce a lot of gammas as well. And so that's going to leave this really strong signal in our detector, which we can separate out. Next, what you may notice is that we have these two kind of parallel bars, one around energy of about 1,000 ADC and the other around 4,000. Now, the lower one corresponds to gammas. Gammas are essentially just a background signal for us. They don't relate to the technique or our interest here. So we can filter those out. And instead, what we can do is to focus on that bar above, which are the neutrons. So here we have neutrons as a function of their time of flight. So essentially, it's neutrons as a function of their energy. And what you may notice is there's a few little kind of notches in that neutron bar, pointing them out with the green arrow here, so you can kind of make those out. And what those are exactly the dips in our neutron transmission spectrum, which correspond to the presence of neutron resonances at those times of flight, which correspond to neutron energies, and hence we can infer what isotopes may have contributed to that reduction in the neutron transmission. So that's what the signal itself actually looks like, and we can go ahead and plot that and again do this inference of the isotopic composition. So here, what I want to show you guys are a few kind of plots. This one's for a range of different elements, some including uranium, nuclear material, and some which are not radioactive. And what we're showing here in black is a comparison of the experimental neutron transmission compared to, in black, the calculated neutron transmission. And overlaid with that in blue is the cross section, the total neutron cross section for those individual elements. So what do we see? We see that exactly where we have those peaks in the neutron cross section, where we expect there to be an increased likelihood of interaction, we see dips in our neutron transmission spectrum. Because for every neutron which interacts in the target, we're not going to detect it in our neutron detector. And so you can see here across the range of different neutron energies for a range of different elements that we see a very good agreement between our calculated neutron transmission spectrum and our experimental neutron transmission spectrum. The other thing you'll note is we have a finite resolution. So as you move further to the right on these plots, you see that we start to get smaller and smaller dips. It's tougher to make out some of those neutron peaks that we would expect to result in dips. And that's just a finite limitation of the technique and doing it in a portable manner, that we have a limited resolution. So conclusion number one is simply to say that we can use this portable DT generator. We can make a setup using that generator, and we're able to resolve resonances across a wide range of different mid and high Z materials. So that's super cool. So now let's look at some of the applications of this for the nuclear security interests that we all have. So application one is detecting uranium and quantifying it. So why do we care about this? Well, what we don't want to do is for folks to smuggle uranium and for us not to be able to detect it. Now, it's a big challenge in terms of quantifying both the mass and enrichment of uranium material, and they continue to pose a challenge for international inspectors and domestic intelligence agencies. Existing techniques, as we discussed before, have several limitations. Vulnerable to external shielding, lead will prevent you from determining enrichment of the uranium. Limited penetration for thicker targets, we discussed that earlier. We generally require calibration to known standards when you have materials and forms that you may not be familiar with. And so our goal here was, can we develop that NRTA setup that we just showed and make it able to both make out the uranium mass as well as its enrichment. So what I'll show you here now is a similar signal, but in this case, there's no target. So this is what we see, just the neutrons, when we have no target in place, the neutrons that are being detected in our detector as a function of their time of flight. And on the y-axis is the number of neutron counts normalized to the minutes of measurement time and microsecond bit width. When there's no target, we don't really see any dips in the spectrum, right? We don't see any energy dependent features. Now, what happens when we add just 1 millimeter of depleted uranium, which is predominantly uranium-238, where you can see that we start to have these very strong resonances. You see these dips very, very strong. And now what happens is we keep increasing the thickness of that depleted uranium. What if we keep adding more and more plates of that uranium and we keep measuring it? You can see for 3 millimeters, we still see that one dip, and now we can start to make out these two dips at higher energies corresponding to lower times of flight. And as we keep adding, we see that those dips keep getting stronger and stronger. And we also see an increased attenuation at the off resonance energies. So here, for just over a centimeter of depleted uranium, you see these three really sharp resonances standing out to us. Now, what we can do is just overlay all those plots I just showed you in a single plot, and we can draw lines that correspond to the energies for those individual times of flight. Now, the thing for you to know is that 6.67 EV, 20.87 EV, and 36.68, these are the three prominent resonances for uranium-238 in the 1 to 50 electron volt range. So these are a characteristic signature of the presence of uranium-238. And so what we saw is that as we start adding more and more of that material, we start seeing deeper and deeper resonances, which make it even easier for us to identify the presence of uranium. What happens if we put shielding, though? I mentioned before that it can be very difficult because shielding can help attenuate the signal that you get. So here, what I'm showing in blue is that 10 millimeter uranium sample. And in red and green, we see what happens when we add 1 inch and 2 inches of plastic shielding. And what you see is a total wipeout of our signal. We're no longer able to make out these resonances. They're totally demolished. We still see some kind of a background signature, but it's not really corresponding to any of the physical features of the uranium material. So the main conclusion here is that low Z shielding, so those of elements higher up on the periodic table, like hydrogen, carbon, oxygen, really attenuate the signal that we can get from this technique. So that's a big limitation. When we put high Z shielding instead, something like lead, here we have the same black and blue plots from the previous slide, 10 millimeters of uranium, but instead now red and green represent 1 inch of lead and 2 inches of lead, 25 or 50 millimeters. We see we're still able to make out those resonances. They're much smaller in magnitude, but they're still present. They're still able to be observed. And so the conclusion here is that for a high Z shielding, for things like lead and those other elements lower down on the periodic table, they attenuate our signal, but the resonances are still identifiable and we can still get a really good signature from them. So what can we do? We can go through that whole fitting process I discussed before, where you'd want to go ahead and infer the target composition. And I have a lot of information here, but I just want to focus your attention on just a few things. On the left-hand side here, we show the uranium enrichment and the uranium thickness, and we're comparing predicted versus true for a 5 millimeter depleted uranium target with a whole inch of lead shielding. And what you see is we predict the uranium enrichment to be 0.1%, which matches the true value within uncertainty bars, and same goes for the uranium thickness. So the point to say here, and you can see the comparison of black, the experimental data, with red, our prediction. And what you see is we have a very good match, even in a situation where we have a full inch of lead shielding that would totally eliminate your ability to characterize the enrichment if you used other techniques. NRTA does let you still make that out. So conclusion number 2 is that a portable neutron generator system is capable of both identifying and quantifying mass and enrichment of uranium, even if it's shielded by up to several centimeters of high Z shield. The other conclusion, which we touched on, is that the system isn't capable of dealing with more than a few millimeters of low Z shielding. So if you know that you're going to have a lot of plastic around your target, or someone may try to use that as shielding, you'd probably want to look for another technique to use. Second application is arms control verification. So what do we care about? What's the kind of research question that we're asking? Well, traditionally, nuclear arms control agreements have relied on indirect means of verification. So on the right-hand side here, you see the delivery planes, the planes which can carry nuclear weapons with their wings broken off. And essentially the reason for that is that if the United States and at the time Soviet Union or the Russian Federation wanted to verify that each country were not deploying too many nuclear warheads in their stockpile beyond what we agreed to in international agreements, well, you could either destroy the nuclear warheads, but that was very difficult to verify. So instead, you use an indirect means of just destroying the planes that would carry those nuclear weapons. Now that's great, but it's not a direct means. You can imagine that they could still, the United States or Russia or one of these nuclear weapon states, maybe if they were lying, they would hide one of these nuclear weapons, still destroy the plane, but they'd still hold on to that nuclear material, which would be very dangerous. So recent arms control treaties have actually started to use passive neutron counting. They've used nuclear radiation detection equipment in these treaty inspections to give you a more direct means of verifying what the other country is saying about their compliance with that treaty. Now, these verification techniques could provide greater confidence in future treaty verification regimes. We've seen a lot of movement on the international side here. And so kind of our goal here is to try to develop research and development plans for developing techniques which can give us an idea of confirming the presence or the absence of the high enriched uranium or the nuclear material which goes into these kinds of weapons, and being able to provide isotopic signatures of the weapons both before and after their dismantlement. If our end goal is to dismantle nuclear weapons and to make that a verifiable part of a treaty, we need the techniques, the nuclear techniques, to be able to do that. So we actually at MIT had a joint collaboration with Pacific Northwest National Laboratory on this technique. So you see the same setup down there, and we performed the first ever measurements with our technique of special nuclear material, high enriched uranium and reactor grade plutonium for this goal. Now, the first thing I want to show you is a plot of the neutron counts per minute in black that we measured experimentally, compared with the total cross section for the target overlaid in blue. Now, this was for a 1.5 millimeter reactor grade plutonium target that included steel and tantalum shielding and a 1 hour measurement time. Now, you see a whole bunch of dips here, right, in this black spectrum, which correspond to those blue peaks in the cross section. Now, plutonium-238 gives a very, very small dip, but we're able to make that out here in the black experimental data. Plutonium-239, which is a fissile isotope, adds a whole bunch of these different dips across our spectrum that we're able to make out. And plutonium-240 gives this huge reduction in neutron counts at around 1 electron volt. So this is super cool. These are the first measurements that we did with plutonium and our portable setup, demonstrating the ability to actually make out those dips in the neutron transmission spectrum, allowing us to infer the presence of plutonium. And now when we do that fitting technique, we can again compare the predicted and true abundances for plutonium-239 and 240, and we again see that we have good agreement within error bars for this target. Again, just comparing the black experimental data to the red fitting curve. So this is awesome. We're able to make out plutonium. The second question is, can we actually do this with high enriched uranium? So here I show the plot for a 3 hour measurement of just under 1 millimeter of high enriched uranium in the presence of plastic shielding. And again, you see that the black dips in the black spectrum correspond to the blue peaks in the cross section. Uranium-234, which is present in just under 1% generally in high enriched uranium, we're able to make out here with a small little dip. Uranium-235 gives a whole bunch of different resonances because it's a fissile isotope that we can make out across this spectral range. And plutonium-238 adds on a little bit of a shoulder to some of these dips, which we're also able to make out. So we can do the similar deal of taking the ratio of the target in to target out, calculating the transmission spectrum, and inferring the isotopic composition. And here's what we get. Again, we see a good agreement between our black experimental data and our red fitted data. And we see here that we again have very good agreement for our predicted uranium enrichment, as well as the predicted total thickness of the uranium mass. This is super cool. These are the first measurements with high enriched uranium using our setup, demonstrating an ability to quantify a range of different uranium and plutonium targets. Now, I'll just go over very quickly. You could imagine if somebody were to replace the weapons grade material in a potential nuclear weapon with something more innocuous, such as fuel grade, could you actually distinguish between those two? Here for 1.5 centimeter of plutonium thick metal, you notice that it's very difficult to do that. The signatures look very similar here. We have a little bit of a reduction in this dip over on the right, but that would be quite a challenge. For high enriched uranium of 2.5 centimeters thick, we see very little transmission when it's high enriched uranium at truth. But if you were to actually change your enrichment or try to decrease the enrichment and maybe divert that high enriched uranium to put elsewhere, you see that it's a very, very different signature that we would get using our technique. So this is super cool because this shows us that there may be an ability to use this technique for verifying the presence of high enriched uranium in arms control applications. So conclusion number 3, it may be challenging to use our setup for a warhead because of the presence of low Z material, which we discussed before. But after dismantlement of the weapon, it may be able to use this technique in order to verify the presence or absence of special nuclear material after separation from high explosive. So just to conclude, now that we've looked through these few different applications, discussed the entire technique itself, we designed and built an NRTA system based on a portable neutron generator. We demonstrated the ability to identify resonances for a range of different elements: silver, tungsten, indium, uranium, on the order of minutes. We explored the system's feasibility for different applications across the nuclear nonproliferation space. We were able to successfully assay or analyze mixed targets, including uranium and plutonium, in the presence of shielding and other elements which have neutron resonances. But we still need some additional work if we're going to use this technique in a range of different environments which are of interest to us. So with that, I want to give a big thank you to everyone on the Zoom call for your attention. And I hope this was an interesting talk, and happy to answer any questions you may have. Thank you.
All right, well, thank you for that really great talk, Ethan. Please, if you have questions, feel free to add them to the Zoom chat, but we can go ahead and go through the few questions we have. So James Indorito from the University of Pisa asks, does temperature of the target material affect the technology?
Absolutely, that's a great question, James. It does, and the main way it impacts this technique is that the target temperature of the material of interest is, I should say, the cross sections, the neutron cross sections for that target material are dependent on the target temperature. So as a target temperature increases, if you imagine doing this for a molten salt reactor for nuclear safeguards, that's at around 1000 Kelvin, you're going to see Doppler broadening of your resonances. So those same resonances that I showed before for that cross section plot, they're actually going to be broadened a bit. They're going to be a bit wider, and that actually may make it a little more difficult for you to be able to actually infer the composition of the target, to be able to separate some of those resonances. But even looking in truth up to around 900 Kelvin or some of these higher temperature advanced reactor proposals, we still believe that we should be able to resolve those different resonances apart at those temperatures. But great question, and it absolutely does.
Right, thank you. From William Redding, would reactor moderator materials, i.e. water, also suffice for NRTA moderation? If so, are plastics used instead simply to save weight?
Yep, another great question. Generally, it can be easier to use plastic instead of water. It's solid. It's a bit easier to ship in truth. And so that's one decision that we made to go with high density polyethylene, but absolutely correct. Water would work just the same. We actually even looked at heavy water, which is deuterium based, but that has some challenges because it takes too long essentially to moderate the neutrons. And so that reduces the resolution of the system, but absolutely water would work well in addition.
Okay, great. From Tommy Tunks, how exactly can you tell the mass of the nuclear material?
Great. So let me see if I can go back to an earlier slide. So when we get to this point here that you can see on the screen, what you notice is that the neutron transmission is an exponential attenuation function. And more than that, it's dependent on the isotopes that are present, but more so their densities and their thicknesses. So you multiply the density with the thickness, you get essential atoms per barn, and that's telling you essentially the mass of that individual isotope which is present. So we look at each of those individual neutron energies, look at the transmission, and then essentially try to do our best job to fit that by inferring the isotopic composition and varying over the neutron mass. So if you have a large presence of uranium-235, there's specific energies at which you'd expect to see a more greatly reduced neutron transmission.
All right, great. Question from Andrew Sally in the chat. Would this technique have potential health effects on nearby observers, or just someone walking through it or in the area?
That's a great question. Absolutely. So all the experiments that we do at MIT are actually performed in a basement vault, which has meter thick concrete walls that we have to move into place before we're able to take and collect any data. So absolutely, it's not something that you could be in the room for example. These portable neutron generators have been tested outside, and actually outside you could have just a standoff distance of probably maybe 50 or 100 meters and still be able to perform the technique. But it's definitely not something that you could do, handheld, for example.
All right, we have another question from the folks in the room at Michigan. Forgive me as I'm not a weapons expert, but why do fissile materials have so many more resonances?
Yeah, I guess the short and long answer is due to the quantum mechanics of the nuclei. But the easy answer is that there's a whole bunch of different processes by which you can fission the nucleus itself. And so as a result, you have a much higher density of states. And so the higher density of states at the lower energies leads to that much richer cross-section region, which you saw. So we saw, right, for uranium-238, these 3 very sharp resonances, whereas for 235 was a whole range. And so that just relates back to essentially your transition probabilities for those different nuclear levels, which are much higher for the fissile isotopes.
Okay, great. One more question from the folks in the room. Some of your graphs showed visible results, even in the presence of plastic shielding. I thought you said this technique was not effective when low Z material was present.
Yeah, great question. You're absolutely right. What I showed for the low Z shielding was for, I'll just go back to those slides just to show you guys. For the low Z shielding, we were looking at 1 inch or more of plastic shielding. So in this plot here, in red, that's a full inch of plastic, and green was 2 inches of plastic. For the high enriched uranium target, there was plastic shielding, but it was only around 5 millimeters of high density polyethylene equivalent. So you're absolutely right. And it's actually a better story than I may show on this one slide, is we actually can handle some low Z material present and still be able to make out the resonances. Here we're saying that there's essentially some limit on how much of that plastic shielding that you can handle. And it's probably around maybe 1 centimeter or so, beyond which you're not able to actually have a measurable signal. But yeah, great question and good attention to detail.
A question in the live chat from Abhishek Pandey. Lead-208 as a moderator, what are your thoughts?
You could use it as a reflector. The main issue is that for high Z materials, in each interaction of the neutron, or each scattering of the neutron, it's only going to be able to lose a little bit of energy, because that interaction kinematically is highly dependent on the relative masses of the 2 nuclei. And so the issue is it's going to require maybe 200 or so or more individual scattering events to moderate your neutron. And the issue with that is it's going to take time as that neutron is traveling through the moderation process. Since this is a time of flight technique, the challenge is we really need to kind of keep that spread in time to be very, very finite. And the issue is if you use even something like heavy water, where you're not even looking at an A of 208, but rather only 2, it's already spreads that moderation distance too much, such that we're not able to resolve the resonances. So you could use lead as a reflector to bounce back in some of those fast neutrons that are generated in the DT generator. And we use it also as a multiplier, as you saw, right around the DT generator to help benefit from the N2N interactions. But it wouldn't work well just as a moderator on its own. But good question.
Okay, there's another question in the live chat from Siddhartha Gupta. For practical situations, does the Doppler broadening mentioned from the temperature have a threshold where it renders the technique inert?
Good question. Yes, I've looked at least broadening up to around 1000 Kelvin, and that still seems to be fine. For our resonances, they're still not sufficiently broadened that you wouldn't be able to separate them out even from near-lying resonances. But it's also in truth going to be very dependent on what your target material is. When we look at fissile materials, or you could imagine even maybe spent nuclear fuel, you're going to have a whole bunch of different resonances from all of the different fission products present, and that's going to be very difficult then. So it's going to be highly dependent on the target itself. But it's probably reasonable to do up to at least several hundreds of Kelvin, if not up to 1000 Kelvin.
Right, great. There's another question on live chat from Modo Nyang. How do you calculate the quantification of neutron? I'm not exactly sure what you mean by that. Maybe you could provide some more detail into what you mean. Mm-hmm. And then there's another question in from the folks in the room. Have you tested this technique for thorium, or is that irrelevant because it can be used for reactors but not weapons?
Yes, that's a great question. Just due to time constraints, I had to actually cut out our thorium work, but we have done this for thorium and uranium-233 samples. Thorium's lowest energy resonance for thorium-232 is around 20 eV, which is within our resolvable range. The challenge is it's near lying to several resonances for both U-235 and U-238. So what we found was we're actually able to quantify thorium quite well when it's just thorium metal on its own. But in presence of significant amounts of uranium-235, it becomes more challenging to actually quantify that thorium. We can certainly identify it and predict its presence, but generally, at least so far, we've been under predicting that. So that's a topic of active research for us to look at this applicability of this technique for thorium safeguards, which I think you may have heard possibly from Oscar in the previous talk about some of their work for that exact application. But great question.
If anyone else has any questions, please feel free to add them to the live chat. But while we're waiting for more questions, I have one.
Sure.
How do you think this technique is going to work in more complex geometries? A lot of this is based on the idea of simple exponential attenuation, but that's not necessarily going to be the case as you move into more complicated sorts of objects that you're trying to do analysis on.
Totally. It's a great question. The first thing I'll note is that for the fitting techniques that we do, it does input some parameters of the target itself in terms of target thickness to perform multiple scattering corrections. Because you're right, the transmission equation that I showed assumes that any neutron which interacts is totally attenuated and won't make it to your detector, which isn't entirely true, especially for thicker samples. There have been some work, some studies in the past done for kind of generalized analysis for different geometries of targets, which provides a little bit of a theoretical basis at least. But in truth, yeah, we haven't explored that as much in our work so far. We've mainly focused on the isotopes itself, but that's definitely kind of a next step for this. The last thing I'd say is that everything that we do essentially it's a single pixel detector. We're not trying to get any spatial resolution here, but the next step would be to actually introduce a spatially resolved detector and then see what the impact there would be. So that's definitely an area, a perfect area ripe for future work with the portable system.
Great, thanks. There was an earlier question more broadly about non-proliferation. I've been told that thorium breeding poses a proliferation risk because fertile thorium is so common as to not require separation from infertile thorium isotopes. Is this concern valid? And if so, why haven't we seen states with nuclear aspirations pursue this technology already?
Yeah, so the big challenge that usually we hear about thorium fuel cycle and maybe some of its inherent proliferation risk, which is something that's kind of hotly debated, is actually the presence of uranium-232, which you produce in the thorium reactor. And that uranium-232, even in only several parts per million, produces a huge gamma background, such that it would be quite hazardous to work with, and also could pose a challenge for your ability to separate that out in producing the fissile material needed for a nuclear weapon. So there's definitely different debates about how suitable that material would be, but it's not a very easy pathway to do. And in truth, there are states that are looking at thorium reactors. In India, one of which has been looking at it for many decades. But generally, it seems that the uranium fuel cycle has been the dominant one.
Just as a follow-up to that, so the
I
proliferation risk concerns dirty bombs, not nuclear weapons?
Well, I don't know on thorium on its own. In terms of nuclear weapon production using U-233, which is fissile, same as U-235, that's one where the U-232 separation would be challenging. If you're just looking for dirty bombs, sure, you could strap any radioactive material to a conventional weapon, and it would pose a challenge on its own. But the proliferation itself primarily would concern to nuclear weapons. I mean, the thorium, yes, you could mine same as uranium, and but I guess we're fortunate to have seen only as few smuggling events as we have with these materials to date.
Okay, there's one more question from the folks in the room. Can you talk about detection methods for low Z moderators? I guess, when this doesn't work for your low Z moderator, what other techniques are there?
Okay, totally understood. So one thing you can do is you have fast neutrons. If you have low Z material surrounding your target, you can imagine that those fast neutrons will be moderated in the target itself and could induce fission if you have fissile material, and that would produce then fast neutrons. So there are folks in the past who looked at using a lower energy neutron source, one that's around 60 keV, so below kind of your Watt spectrum for fission. And essentially you could just put those 60 keV neutrons on a plastic shielded target, produce any fast neutrons. And if you put a fast neutron detector, presumably any of those fast neutrons would be generated from fission in your in the target itself. So there's a range of different techniques that are looking specifically at those fission neutron signal. You look at differential die-away as well, for example, where you essentially send in the neutrons, induce fission, turn your neutron source off, and then look at the kind of die-away of that signal as a result, and it'll be much more pronounced if you have fissile material to carry on some of those neutron-induced reactions using the moderation of the fission neutrons in the target itself.
Great. There's a follow-up from Moto and Yang. My question is, how do you calculate the quantification, for example, plutonium detected by this technique?
Right. So let me see if I can go back to this slide. So essentially what you can do is you can make a we have very good nuclear data for almost all isotopes for their total neutron cross section. So you can get this calculated neutron transmission as a function of neutron energy for an assumed composition of a target, where I represent the different isotopes present with their different quantities. You know your system resolution function, you just convolve those two, it's just a mathematical operation. And now you get a calculated transmission of what you'd expect to see in your experimental data. Now, what we can do is we can define an error term here, which is the difference between your calculated neutron transmission and your experimental neutron transmission. And what we can do is we can start to alter the different, to vary over the different isotopes present and their different abundances. And we can see which combination of those gives us the least error between our calculated transmission and our experimental transmission. And so that will then let you get, based on this least squared minimization, if you have some inference as to which isotopes may be present, allow you to get then a predicted composition. And that's exactly what we used for those slides that I showed later, where we got the masses and enrichment and showed that fit of the red curve to the black experimental data. Essentially, we said, we think there may be uranium and plutonium here. Let's have this fitting routine to try to minimize the error between the calculated transmission and what we saw experimentally.
Okay, there was one last question in the live chat. For what kinds of elements can we use NRTA? And I think you have a periodic table graph that more or less shows which ones have some cross sections.
Yeah, so I'll throw that back up very quickly. So here's what you can see. The main thing to note is that for our technique, you can certainly do things under 10 EV. So any of the elements here that have these black triangles are suitable for our technique. We can do some of the ones between 10 to 100 EV. We can make out stuff up to probably around 50 EV pretty reliably. But one thing to note is also this is a periodic table, so it's only showing the elements and not showing individual isotopes. So as we showed before, uranium here is shown as one block, but there's a whole range of different isotopes, and each one has its own kind of isotopic signature. So it is a whole range of different elements that we could look at. Which is great because it also includes stable elements such as silver or gold, for example, that we can analyze even without it requiring it to have some radioactivity to do radiation detection.
If there are no other questions, I think we're just about at time. So thank you, Ethan, for the really great talk. And if you have any other, if anyone else has any questions, I'm sure Ethan would be happy to answer them later if you can get his contact info. So yeah, thank you.
Great. Thanks, everyone.